Okay, well, thank you very much for this introduction. Really wise words and there's much content, which is extremely important to remind to all of us and to the students who are here forming the future naval architects in this world. Well, my name is Guilhelm Gaillarde. I'm coming from Marine. I'm extremely glad to be here in person this year. We have started this journey 3 years ago with a simple idea. With several people in the room here, how could we, let's say, try to transfer some knowledge from Europe? You mentioned a lot of what's happening in Europe at this moment, engineering here in the US, and how could we inspire students to create the ships of the future? And we set up this conference, and I'm very happy that's the third year now, and well, really looking forward to hear all the papers. This first introduction, I would like to make, let's say, an overview of where we are at this moment, especially what Marine is doing at this moment for part, but more, let's say, also background and a global picture on how we are with sustainability and sustainable development for ships. Of course, I'd like to start with the most important of all, our blue planet. And always good to remind to people, I mean, I don't have to hammer that with naval architects and people busy with maritime engineering, but always good to remember that it's called Earth, but it's actually a blue planet. 70% of the surface is covered by water. There's also quite a big deal of water on Earth, which is present in the oceans. And also, as you know, 90% of the world trade is transported by sea, so 80 to 90% depending on the type of trade. Well, that shows how important is our sector, and which is not always, let's say, in the highlights, in the most prominent place in the news for the energy transition, but it really, these numbers shows how important the maritime sector is. We have to deal with 200,000 ships about worldwide, with gross tonnage of more than 100 gross tonnage. Well, that's a lot to transform because we know we'll have to come with a new generation of ships. We'll have probably to refit a lot of them. So it's quite a big job. And maybe also important to know that 7,000 of those ships are transporting about the health of the all transport capacity. So you could say that's a lot. That's also a niche market when you compare to air transport or a car transport, for example. So, well, that's our task, to transform this sector, and we hope we will contribute to it. Also important to remind that global emission from shipping is about 3% of the total from all the activities on Earth. So comparing the amount of activity with the emission, I mean, we are not contributing so much, let's say, at least for GHG emission. The issue is that, well, this number is expected to grow to almost double in the coming years if we don't do anything. So we see that all the maritime sector is really, really active at transforming its energy and also taking his share, maybe because of the close link with the ocean and Earth on showing examples, despite the fact we are not always, let's say, the prime interest for many regulations. Just looking back, because in my discussion, I think when we started 10 years ago at Marine talking about sustainability, things were quite clear. And I have more and more also from industry some discussions about why are we doing that? Only 3%, and what's the big deal? And Earth has been also warmer earlier. So, okay, why are we caring about? So just wanted to put that a little bit in perspective. There's been some recent studies showing the relation, clear relation between carbon dioxide and temperature on Earth. Of course, there are some times where Earth was much warmer than now, but life was not maybe a little bit not so easy. But what is at stake at this moment, as this change which is taking place, is just too quick, too fast. So we will probably be able to adapt as people. We'll be smart engineering to adapt and to go against rising sea, for example. But the rest of the nature might have a really hard time. All the changes that occurred on Earth over the last, that's a recent study from the last 60 million years, happen in the order of 100,000 years to 1 million years for the quicker change. Now we have really changes that happen at an incredible rate, which is extremely worrying. Well, you know that part, relation between our emissions and average temperature. this is what we are talking about, a very large rate of, let's say, CO2 and other gases are just pouring the atmosphere. That was also the origin of our wealth, of our development. So we cannot complain about it. We have built incredible ships. We are transporting an amazing amount of goods with fossil energy, but it has a drawback that we realize right now. What you mentioned, all the countries are contributing to different level. Actually, I don't find this map very fair, because the two biggest, let's say, countries emitting GHG are also the one having most activity and highly populated. So it's not a very big surprise. But it's true that if we want to make things happen, we have to start with those countries who are responsible for quite a lot of emission. The other message of this map is that all the countries are concerned. So it's good to see that many activities and many initiatives are taken worldwide, because it's also a worldwide consequence. Looking at the total energy and total emissions per sector, well, if you want to find maritime, it's very small. It's only a few percent of the total. And also, this is a picture at European level for domestic maritime sector, 0.4% of total emissions, 3.6% accounting for international shipping coming in European waters. So it's not a very big stake. But what is happening is that maritime is present everywhere, and we are taking care of transporting about everything which is transported on Earth. So if we can, as a sector, transform ourselves, that will surely have a consequence on the rest of the other sectors. We are a kind of hard to at that sector, because we need a lot of power for ships, but we have a big advantage compared to air transport, is that we can also manage a little bit of more displacement and volume with our ships, but still we have quite big constraint in terms of autonomy and range, especially with new energy carriers. So on the good part, this is also to remind, because we read in the press, and maybe you hear that also in your sector, that ships are polluting incredibly more than any other means. Always good to remember that when you look at the number of transport capacity, ton per kilometer or ton miles, maritime shipping is by far the best way to transport things on Earth. Better than rail, better than inland waterway transport, better than trucks, better than planes. So I think it's important to remind that, especially sometimes at political level, because, well, they are making the rules, and we need to be helpful in that respect. That was also another view on who are the contributors, but who are, let's say, the people to move, let's say, to transform the fleet. This is a different map. Then you see that, well, Greece, China, Japan, or Singapore, Germany are countries with quite a large share on, let's say, owning the ship and the fleet. And also we have to target these groups to convince them to move. I like to come back also to a little bit of definition of emission, because we have, I mean, ships can emit many things. We have emissions, let's say, that are close to, let's say, have a climate impact. That's all the series of greenhouse gases. So the most well-known CO2, but also methane, fluoride gas, and N2O. All the type of emissions are more related to air quality, and you have to think about sulfur, and SOx, NOx, fine particles, and very often in the public opinion or in the news, those two are mixed up. So there are different types of conclusions taken for how bad are ships. Other type of emissions which are taking a large importance at this moment. This is underwater radiated noise. This is also let's say, the focus is also increasing at this moment with more stringent rules, also local regulation to reduce the level of underwater noise. We have solutions for the shipping. I mean, you can turn the design of propellers and hulls and try to, let's say, have suboptimal designs to reduce the noise. But it's going to have a very large impact on wind parks as well. There are upcoming regulations for a kind of level, average level per year of noise emission for wind parks, including installation. And this is producing a lot of noise. So those type of regulation, of course, has one part that they are here to protect mammal life at sea, but it's to also add some constraints in the design, and not only design, but also in the operation, how you're going to develop wind parks and install them. Well, just notice I just mixed up two types of emission. So I was just talking about the URN, the water radiated noise. The one I just presented before were the radiated waves. These can also have an impact on sediment and coastal erosion. And it's really dependent on the place where ships are sailing. Some work that we're doing quite a lot at Marine since years is working on the Vaporettos, the ferries sailing in Venezia. There's obvious requirements on type of waves and steepness of waves and magnitude to try to reduce the erosions on the buildings. But I mean, you can see that also on certain coastlines where there's a lot of traffic and where erosion can become a problem. The last part that I will not deal with is, well, say more wake signature magnetic infrared. That's more domain, well, let's say more important for Navy side. It is also part of the emission of ships. I like also to just deal with some of these headlines that we see a lot, and we hear that from our friends, let's say personally, family, also in the news. And it's like almost sometimes look like shipping bashing to try to have these headlines, health risk for shipping pollution, statements like massive container vessels equal 50 million cars in terms of emission. I don't know if this has playing let's say a lot in the headlines in US, but in Europe that has this type of news had quite a lot of impact. So big headlines from different newspaper, but you also see that it starts also to influence on the political level. And we've heard this type of statements from people from the parliament who are making the rules. So it's very important to be very clear with the facts, to do fact checking, and try to avoid this type of quite big claims. So there has been a study done last year by SISDO to pick up all of those claims and try to put some numbers and fact on it. And I took a few of them only. I gave in the presentation a reference to their good report. Unfortunately, the full report is in Dutch. They've got a summary in English. But if you have some questions, just ask me, I will tell you. But I pick up a few examples that was stated already in 2014, but used back again during parliament decisions and discussion about shipping. The fact that 16 largest ships emit as much CO2 emission as all the cars in the world. That's pretty big statement, and this had quite a big impact, I must say, on many discussions and many preparation in a regulation. SISDO just made quite some calculations and spotted the 16 largest ships in the world, which are responsible to about 1 to 4 million tons of CO2. That was calculated and data available in 2015. And that's actually equivalent to about 2 million, and all the cars in the world emit about, between 2,000 and 3,500 million tons of CO2. So actually the 16 largest ships produced as much CO2 emission in 2015 than 0.1% of all the cars in the world. I think it's very important to stress this because these headlines are really make sometimes things very difficult for certain discussions, especially with authorities. Other parts, and we also have to be very critical with our industry. This was stated at the Dutch Parliament in 2017 that the 17 largest ships in the world emit more sulfur than all the cars in the world. I don't know what this is with all the cars, but it seems to be a very important benchmark. That is quite close. So ships are really emitting a lot of sulfur. Real calculations, it's always difficult to say what is a large ship. Is the one polluting the most, or is it the largest capacity or the largest passenger capacity? But if you take a kind of wide definition of 17 large ships, they emitted around 10 to 45 kiloton of sulfur in 1 year. And if you take the almost billion cars worldwide, we have different also criteria in terms of emission. That was about 70 to 350 kilotons. So it's not like 1,000 difference with CO2, but it's getting quite close. There has been also this type of hate news from the Daily Mail online, 2009. Also, this type of news used a lot on the political sphere. The study showed that it's quite difficult to make the statement because the rules are changing. Let's say the content sulfur at that time was 300%. It has moved back to 2.45%. There's also control area where sulfur is being reduced. Also, the fuels are changing, and all the cars in the world are not equal. So it's extremely difficult. If you take the worst of one part and the best of the other, you can make this type of statements. But something more correct would be, and it's still, I would say, quite enormous, is that one large container vessels of capacity of about 14,500 TU would emit about 1 kiloton of sulfur. That were data from 2015, and this is equivalent to between 3 to 12 million cars in a year. So, okay, this is quite a lot, and you understand also why some regulations need to improve, especially large cities or also harbor cities who really suffer from air quality problem, like New York, like Mumbai, like Rotterdam. This is a big health issue, and for that we really have to be critical as a shipping sector. Another claim also from a political party in Holland about container ships polluting as much as 50 million cars. Again, looks like the same sentence is reused and reused. But in terms of NOx, it's still a lot, but not as much as they claim, because let's say one large container vessel emits per year as much nitrous dioxide than about 250,000 cars. Still a lot. If you try to solve an emission problem for air quality in a city, it's easier to target one ship or one big cruise ship coming than a few 100,000 cars. So we have to do better. We have to do more, but it's important to know what we are targeting in our changes. So coming to the, let's say, to the core of the presentation about designing sustainable ships, we need to have a very holistic approach. We used to work on specification, on trial condition, and we are becoming very good at, let's say, having a target-based design for independent criteria. We can reach the speed we hope. We can have incredibly efficient propellers. We can also have suspended engine. But if we want to do something on sustainability, we really need to take the full picture. And I'm very happy that we are also joining design and operation, because one without the other is just impossible to solve the issue. So we have to work on ship design, of course, but we also have to work on ship operations. But it's not only the ships, it's also the fuel infrastructure and the transport infrastructure. And at last, also fleet and logistics. So it's very difficult because all the roles have been, let's say, optimized through the years between naval architects, ship owners, let's say harbor operations, trading, or energy sector. But we need to bring all these parties together to make a move. I would just use a simple parallel from, let's say, implementation of electric cars. Without good, let's say, charging infrastructure for energy and a decent price, you cannot introduce electric cars in a country. Some companies have understood that very well, and they're successful. And we miss this type of approach at this moment from the shipping sector, which is very much separated between every specialty. There are three main drivers behind this, let's say, revolution we try to do is just we have to use sustainable energy. There's no doubt about that. We need to do something different than fossil-based energy. We also need to change our design strategy, really design for operation and not design for trials condition. And we basically have to use less energy, much less, because the energy content was a gift for fossil. I mean, there's nothing better, maybe nuclear energy, but with other type of issue in terms of energy content. But all the other alternatives do not have the energy density of fossil. So we'll run very quickly into a range problem or capacity problem on board, and we have to really stress that we need to use much less energy to make the transition. And well, the last one, use just fully available energy like wind. This is obvious, but I can tell you that 10 years ago, that was a very hard discussion. A lot of people find it very nice and pleasant, but not very serious. What you mentioned, broadly with the current development, we are showing also the world that we can do very serious things with wind. Starting about sustainable energy, I will try to speed up a little bit, sorry, but I still have quite some slides. Just to remind the basics of the approach taken at this moment at Fuel EU regulation in Europe, but also brought to the IMO working group on sustainable alternative fuels, the life cycle assessment of our future energy use. So not only looking at the emissions we produce while using the fuel on board ships, but how the fuel is also produced, to have a complete assessment of the emissions from well to wake. So from the resources up to what we deliver on the propeller. There has been a lot of debates about that. I was part of a few discussions at European Commissions to try to push that forward, because everybody thought like, no, holistic. I mean, the energy sector is doing his job and we are just using the fuel. We cannot be accountable for the fuel we are choosing. Well, at the end of the day, quite happy that life cycle assessment and well-to-wake approach is being used, because it puts everybody facing his responsibility, and it will also imply that energy part and shipping part will have to work together to make this happen. So we basically have different types of resources on Earth: fossil for a big part, biomass as well, metal also to produce nuclear energy, and different types of renewable energy. We are able, with different types of process, to create from these resources about any type of molecule. The more complex, basically, the larger the energy content, also the more expensive and the most energy losses. But basically, with all those sources, you can, with certain production process, create diesel, also synthetic diesel, but it's a complex molecule, C12H23, so that's why it's so rich in energy, but very complex to make if you don't get it for free from fossil source. Also, methane can also be synthetic or created with biomass and different types of process, LPG, ethanol. And then we are coming more in dimethyl ether methanol ammonia that can be made out of hydrogen or not. And we also have different types of more, let's say, exotic, not yet really at very high TRL level, liquid organic H2 carrier, formic acid, or sodium borate. So there are many things we can do. Incredible. I mean, we don't like ideas. We don't like forms of energy. And this is maybe a problem, is that we have a hard time to find which one will be the good one. Because when you make a choice and you're going to build a ship for 30 years of operation, it will be barely possible to change from ammonia to methanol or to methane, for example. So this is part of the issue. Then we have to convert this energy on board. We can also combust the energy. We are back to internal combustion engine of different size, or we can just use the energy as electricity storage and through a fuel cell produced by electricity on board. And we see at this moment a lot of gravity from yards. I mean, it will be announced, I hope published in few months, but there are projects with liquefied hydrogen on board certain ships. Storage is quite a challenge. We also have compressed hydrogen for certain application. But we also have Gaillarde, has published already, San Lorenzo, yacht builder in Italy, who's have a storage of hydrogen into methanol. So you have methanol on board that can be atmospheric. You can just store it into tanks or special tanks, but then you reform it into hydrogen on board. So you already have extra machinery. The hydrogen you put in the fuel cell and electricity. So it's quite a complex route on board. But I mean, some believe that it will be better for bunkering. Methanol is kind of easier than hydrogen, but you need, well, you don't let the complexity on the shore to do all the transformation. You bring that on board. I'm not sure how far will go these solutions because they ask a lot of complexity on board. On the other hand, I mean, we see a lot of shipyards and designers taking initiative to do something, and this is nice. I mean, they're exploring, and future will tell is it the right solutions or not. And well, at the end of the row, we have to still hopefully then and distribute this power to our shaft line and propeller. I had a bit of a hard time at the beginning to put the lower part in this table because that was proposed at the European Commission. They say, well, wind is not a commodity. You cannot store wind. So wind is good for energy reduction. But I told them, no, wind needs to be put here. It's also an energy carrier. Okay, you cannot store it. It's not a commodity you can have on board. And you don't pay for it. So it doesn't fit in the picture, but you can also use it as primary or secondary source of power. So wind is also at the bottom, hopefully in this picture. Just to remind that often maybe it's not needed anymore, but we can have the most direct, let's say, drive from electricity to battery and electricity, let's say, direct electric drivetrain. This is by far the most efficient in terms of energy losses. You have a little, and you produce not so much greenhouse gas emission. If you start from renewable, storage battery, even counting for the manufacturing of batteries and recycling, and then direct drive. And you could put that almost as zero. Let's say it's never zero, but very close to zero as total emission well to wake. If you get your electricity from coal, you're not polluting on board, but the amount of total emission you produce is actually more than using MGO. Marine gas oil. So many people tend to forget that, but if you're in countries where there's a lot of electric cars, but where electricity is produced from LNG or coal, then you have good conscience, but for her it doesn't mean anything. It just produces as much greenhouse gases. So that's why the well to wake or the life cycle assessment is a very good measure to do something about the problem. Same thing for ammonia. Ammonia is maybe the most extreme case because ammonia produced with, which is very trendy at this moment, produced with renewable electricity is quite costly, but has a very good, let's say, very low level of emission. When you produce ammonia from fossil energy, it's about 6 times more emission, 6 times more than you're just using marine gas oil. So you hear sometimes, okay, we're going to use ammonia and gray hydrogen for 20 years because it will prepare the transition. But that means that in 20 years, we will be multiplying by a factor of 3 to 6 our emissions to reach the goal that it will just be too late, I'm afraid. So this is very important to understand. This is what my colleagues called the French spaghetti at that time. I tried to, through a portal, to have a clear view because it was very difficult for us to understand how can you produce with watts and at the end what do you bring to your shaft line. These are about 75 possibilities of pathways between resources, conversion, energy carrier conversion system up to the shaft line with different results in emission. We only listed here about 70 to 80. There are maybe 200, 300 ways, pathways to produce something. And this is showing why it's very difficult to ask ship owners and shipyards to take a decision, because which one is the good one here? It's an extremely difficult question. Energy density is a challenge, and this is just to illustrate that. This is, let's say, short sea shipping container vessel, a design we worked on. I don't have the version with MGO, but the engine room is even smaller. So we went to a version with electric engine and batteries. Actually, part of the containers are just containers full of batteries, so you miss part of your payload. And the bottom picture on the right is the equivalent with hydrogen, so you lose even more payload. So you can have the energy on board. There are solutions, technical solutions to do it, but it has a direct impact on your payloads. So it's earning capacity on the side of the ship owner. It's also space and net tonnage for the naval architect. And those questions cannot be left behind during the new, let's say, ship design spiral. The type of energy you will choose will almost govern the way you will build your ship and think about your space on board, and even raise questions about autonomy, range, and displacement. Several projects started 10 years ago with letting these questions behind and say we'll always find space to put a cooling system, we will find a way on the deck. All these projects just never finished. The building was never done. There's one good example in Amsterdam, in Canal. This question had been left on the side, and at the end of the day, well, the yard realized we don't have space and enough displacement to fit all the equipment on board for our fuel cells. So this is very different because we asked our naval architects colleagues to also know something about power systems and power management systems, electric system, energy. And we need to call and to have different specialists there to help us at concept level to, from our input of what should be the performance of the ship, what should be the constraints in operational operation, to guess and to calculate how much power you can install on board, in which form, and which type of energy carrier. And you really need to study that because many options will be discarded. You just cannot put that on board, or you might have to discuss to increase the displacement of the ship or the length or the width, or to change the operation because the range will be different. But this is an extremely important point to raise very, very early at concept stage. Another point about OPS, a large part of the emissions, especially sulfur NOx, happen when the ships are cold ironing in harbor. We have been asked by Harbor of Rotterdam to do a study and to look with them about, okay, how can you do that alternatively? So what ships are doing at this moment is just, okay, having their energy carrier bunkered on board, and they're running their engine, and they are producing about, well, 500 grams to 1 ton, 1 kilo CO2 equivalent per kilowatt hour consumed on board by the hotel load. Well, this is a lot of emissions, so CO2, but also a lot of sulfur and NOx, which is good, bad for the air quality. There has been some options to also use UPS with direct shore power. So you need to do some fits on board. Well, you mentioned at this point that in US, there's less technological development than Europe, for example, for sustainable shipping. But for OPS and onshore power supply, US is doing much better than Europe. There's been few regulations, especially in California on the West Coast, where it's just compulsory since 20 years, and ships have just adapted, and they find a way to plug the ships in and reduce the emissions. There are still discussions in Europe, so everybody says, just vote it, do it. And the maritime sector will do it. Hapag-Lloyd, for example, which is operating on the west coast of America, but also in Europe, just tell us to do it, we will do it. We have the solutions, and there's still discussions because, well, politics, maybe interest of different harbors who are competing, and not the possibility to add a regulation at the same time everywhere, but it's still on. Still, if you produce the electricity that you will provide the ships with fossil, then you will just produce the same amount of more emission, but just upstream, not in the harbor. So it could be good for the air quality in the harbor, which is often close to a big city, but for, let's say, global aspect, it will not help a lot. So you solve a local problem, but not the global one. Another solution, of course, the most obvious, is to have the whole system OPS from renewable electricity. So that's also possible, but it's hard to store renewable electricity. And this is by far the system that have the less energy losses. You lose about 11% in the whole thing, and the costs are pretty small. Other option can be to have alternative sustainable energy carriers based on renewable electricity, put them on the ship, and the ship will produce its own electricity. It's also possible, also not much emission, but you lose about 60 to 85% of your renewable energy to start with, which is quite a pity. But things are changing, and I think since the last conference, the first conference we did, then well, you see that Guilhelm, for example, in Rotterdam, made a really a giant step. They have two very large platforms that are used in the North Sea for installation and decommissioning of platforms. In the winter months, 4 months long, they cannot operate in the North Sea. Weather is too harsh, and they are just onshore in Rotterdam, close to the center, just burning fuel and polluting massively the whole area. They decided to change that, so they have put a power connection of 20 megawatts 2 years ago and connected it to 12 platforms to the grid. Well, that's something because it's like 15,000 homes, so you need to improve your infrastructure and energy infrastructure, so it's not a small thing. And that shows how it's important to combine the infrastructures and hardware infrastructure with our pathway to sustainability. So what they say it's about, let's say, a yearly emission of 5,000 diesel cars, so that the air quality since that moment, just plugging in, improved a lot. Well, there's still a lot of cruise vessels going there. Queen Mary were there just a week ago, so these ships also should be plugged in a way. Design for operation, on that part, I will go very briefly because I think I showed that 3 years ago also. There's no much changes in the principle, but basically you need to know as an architect how the power, how the energy is used on board during operation. So it's not only a few specs, but it's also interviewing the crew, the captain, looking at the backlog and the information about the operation, discussing if the operation can be different. But you really need to know how it's going your power and how you use it and how long, because that will provide you the dimension of your solutions on board. Well, this is a typical inland, it's called inland patrol vessel in Netherlands, but it's also a bit of coastline because, well, there's not always a clear difference between the coastline and inland there. So the ship has to do some endurance time with given power and also some surveillance and different region. And you really need to look at how the power is consumed and the energy to be able to have the right solutions. This is a way we are doing it. So you're starting on the left side is the diesel combustion engine, simple, which have the smaller weight and volume on board. And you can always add things because there's room enough. And you see that all the alternatives that fulfill the operational criteria in terms of range or speed are thinking basically more space and more weight. Up to a point that, for example, for battery electric in that case, or even for liquid, let's say low temperature PEM fuel cell with hydrogen, it just doesn't fit in the available space. So you have to do those studies. It discards a lot of solutions that could be really interesting in terms of performance, but it just doesn't fit. Or you need to go back to the design loop and say we need a bigger ship to do the operations to be able to fit that. So this part is really crucial in ship design. Looking at macro perspective, as I told you, we have to always now in the recent study to combine the energy part, infrastructure, ships, and operation. We have done that in a recent project at European level to try to simulate on a 30 years lifespan the whole network in a region. So this is an example for Greece, where we, let's say, simulated the all 860 vessels doing transport between islands, so goods and passengers during the whole year, during 30 years long. And then we looked at the operation with diesel. So we have the data, it's just working. There's a certain emission level, certain cost. And then we have been looking at strategies. And what was very interesting there during the discussion, because we are doing that with the Greek authority, is that you have questions related to the shipyard and ship design. Okay, we're going to transport the small dot going from island to island and only change that. And then you come for the first constraints, okay, with where the energy is coming from. And then you have to talk to the harbor. Can you imagine to provide and to implement this amount of energy in 10 or 15 years? And then you discuss with the ship owners who say, well, can I pay that? What is the prospect on the energy price if I commit myself to electricity? Well, will the price will remain constant or is it going to fluctuate like the last year, especially in Europe, where electricity has been almost being multiplied by 4 for certain sectors due to the impact on of the war in Ukraine. So all those things, uncertainty or about price. So that will have an impact on investment and decision about infrastructure. We'll have backed up by harbors and authorities to provide me with the energy where I need to have it, and also the decisions from shipyard and ship designers. The three have really to work together to be able to implement a solution. So we are working on many, let's say, simulation of that. There's also the first stages are available online. What is interesting is not really the results that are the most interesting for us, but that were the discussion that led to the different scenario. Because we realized that everybody around the table creating a scenario was just pulling, oh, I can do that, but okay, the problem is yours. Oh no, I can do that, but the problem is yours. So they had to agree on a kind of common strategy to be able to implement changes. About using less energy, that was also one of the important aspects. Hull optimization, aerodynamic performance will remain very, very important. I heard a few years ago that we have been optimized so much the ships now, and we know how to do it with CFD and all the tools that is just like polishing the stone. This expression was very much used. Like, we know how to do it, there's no need to do more. You know, we have good ships now, but it's not true. We need to keep being very, very, very sharp with ship performance. So aerodynamics, don't forget it, it's extremely important. So that the students keep working on aerodynamics, we need to have good performing hulls. Also good propellers. We can do an awful lot of simulations. The art is always to find a compromise and find the right propellers. Then last but not least, use free available energy. And wind is just one of, because the most sustainable energy is simply the energy you don't use. And this is really important. What we see in the trend is that retrofit for large ships that will have about 5-6% reduction in energy need for the operation, because you put wind devices on ships that were not designed for, so they can also not cope with much side force. Then we have new builds, short terms. Well, actually this is all because this one is already in operation since last week, but you could reach up to 20-25% of energy efficiency. And then you will have the next generation of ships that will be mainly wind propelled, and they can really reach 60-80%, 85% of the energy only with wind. But you need to adapt a lot of things, including the type of operation. In terms of aerodynamics, many things will change also in the study. Well, you will have asymmetrical flow in propeller disc. So propeller design will have an extra dimension of complexity, also appendage design, and we'll have a lot of, let's say, asymmetric flow optimization. So that will be even more difficult, because it's not only finding the best compromise in speed, range, and draft for certain operation, but also combination of heel and drift angle for the hull form. So that's going to be quite a good exercise to find the best compromise again for this type of ships. What will basically change? More draft for ships, because they will have to have deeper hull to counteract the side force of the sails. More U-shape, so V-shape, U-shape, and flat up body, great, but not when you're sailing at even a slight heel angle. So V-shape more important. Or with flat stern, so work more on the appendages, on skeg and bill skills, and high lift rudders, for example, or even decker boards. So all these things will have to be put into the design. Well, this is something I showed already about the performance of ships improving. So these were, let's say, still calculations done a few years ago between Europe and Guyana, and we hope to reach with different, let's say, wind assistance on existing ships between 5 to 40% of emissions. Has been calculated a long time ago. We are very happy now that the first ships are being built and starting their operation. Cross finger, but I hope and I trust that they will also prove and show that those calculations are real and they can really reach this type of performance. This is one that I hope will have a big impact on the shipping, especially cross-Atlantic shipping. That's a project Neoline, where we hope to reach up to 75% reduction for the same payload capacity, but with a longer crossing, going from about 5-6 days to 12 days. but being able to carry goods between Europe and America with 75% reduction in emission. We will know about that one in about 2 years. Ship is under construction, and I hope in 2 years we'll be able to come back with confirming these numbers. So again, using sustainable energy, very important. Optimize the energy operational profile and know it. So you have to go very early in discussion with the user of the ships. Only designed for operation, not for trial speed anymore. Work on the infrastructures, use less energy, and use wind. These are really the important takeaways for ship design of the future. We had shown this type of pictures a few years ago, all nice computer generated picture. We also used that one, the canopy, for our first conference. So we were quite proud. We thought, yes, we're going to have some ships, but the route is always uncertain. And I'm very happy because it's quite a coincidence. But last week, this ship made its first crossing, transatlantic from Europe to Guilhelm. And one of my colleagues was on board. And this is just a picture taken from a drone, which is less than a week ago. So it's not yet in the press. So it's really something new for today. And they have had a wonderful crossing. It's always surprising to see that the concept picture is almost identical. So I can promise you the right one, that's fake news. It's a real ship and a real photo. And they have been instrumenting the ship, measuring the performance, and did a wonderful crossing. So we cannot present yet results. They are, let's say, crushed. We're going to work on it, but I trust and I hope there will be a lot of publication. But this is to show you that it's possible. We had ideas, we had a wish to change things, and this is just happening with several initiatives. But we trust that this initiative will really inspire many ship owners to change the way they design, and they want us to design and operate ships. Some words to finish. Success is not final. Many projects show that. You need to keep on working to convince. Failure is not fatal also. Just try again. It's never there, but there's courage to continue that counts. And the ones who are putting these ships at this moment into service are very, very courageous people. I can tell you, they don't have much funding. They have a lot of critics, but still they do it, and they find the right way and the right contacts to do it. But I mean, chapeau, because it's really not an easy way to do that. And always remember that simplicity is the ultimate sophistication. I see many, I mean, we are used to high technology, and we often think overcomplicated. We think that any control system can help, that you can control or correct any mistakes with additional complexity in engineering. I mean, try to think simple. Simple is good for ships because it's a very harsh environment. So there are many complexity in many solutions with energy carrier, transforming, etc. But try to make sound and simple engineering, and that will stand on board ships for quite a long time. Thank you very much for your attention.